So today marks a special holiday in my culture. So when this comes out February 1st, it is Chinese New Year. So for anybody speaking Cantonese, 恭喜發財, and anybody speaking Mandarin, 恭喜發財. So I wish nothing but the best of luck and wealth for anybody looking forward ahead of the year. So I thought today's video that we might do something a little special for fun, and I picked out a contest problem from the 2007 China National TST, the team selection tests or examination, which these are usually tests issued to the top finishers of the National Olympiad, where they'll be able to compete for the International Olympiad, just like the IMO, for example. And so the question is to find all functions f that maps from the positive rationals to the range positive rationals, such that the functional equation we have satisfies is f of x plus f of y plus 2xy times f of xy is equal to f of xy divided by f of x plus y. So the way this video is going to be divided up is there's actually 4 different parts. So usually when it comes to solving functional equations, there's usually more of a guess and check, which of course that's the plan to be doing. Then we actually kind of just work our way up from starting with some number, like for example, if we're dealing with like the base case generally is 1, which is a good guess and check to see, or 0, and that's, or in another way. Then if we just work our way down to see that if we can actually get something with, the mapping such that our variables accepts only positive rationals, then we're actually good to go from there. There's a lot to intake for this proof because there's a lot going on here. So what I'm going to do for this video, usually I don't erase content. I like to keep everything like together as one, just to make myself feel like everything is put together like easily. But since there's so much going on, we're going to split 4 different steps of approaching this proof into like one at a time. So I'll put in the first step, everything here. After that we move on to the second step and I'll erase from the previous, and then so on and so forth, and we get to what we want. And as a little just for fun, by saying this, you might be thinking, don't you usually write your texts or like everything on the board in black? Well, because everything is in red this time, because the color red, it means, is a special color for the Chinese culture. Specifically, red is supposed to symbolize good luck and wealth, prosperity also as well. And we also, and for all the children's out there, we actually receive these hongbao, which is red envelope that's filled with money. It's actually also as a way to like wish them, wealth and prosperity as well, good luck in the New Year's. But also the color red itself is another way to, ward off evil spirits within those tales. So I thought just for fun, we just write everything in red. So it probably might be a little hard to follow. I apologize for that, but I'll try to explain everything I can one by one, so at least everything flows and it's also coherent at the same time. So happy Chinese New Year. Just say that one more time. I wish you guys all the best of luck. I wish my family, my friends, and to you viewers, the best of 2022. Eye of the Tiger. Or just kidding, it's actually the year of the tiger. I'm just said that just for jokes. Yeah, let's actually jump in. Remember I said that usually when you deal with functional equations, you would like to do like more of a guess and check to see like some sort of pattern. The first thing we're going to do is rather the first step of this entire process of trying to find our functions to satisfy the functional equation. We first want to start off by showing that f of 1 is equal to 1. So I'll say that proof that f of 1 is equal to 1. So by doing so, let's actually suppose we put y is equal to 1, and we write the function f of 1 as a constant. We'll call this a, lowercase a. So then what I'll do is we actually just plug in the following. So we plug y for equals 1 over here, and then that will be that f of 1 is equal to a. So we'll notice that we'll have f of x, then add this with, so plug 1, so that'll be a, then add this with plug 1, so this will be 2x, then multiply by so 1, so f of x is simply just equal to, so this will be f of x on the top, and then on the bottom the denominator would be f of x plus 1. And so what we want to do is we'll actually get f of x plus 1 by itself, which is very easy to, you know, perform the manipulation over there, the algebra, and you'll get that standalone that f of x plus 1 is simply just equal to f of x. Then we divide this by, so I'll factor out the 1 plus 2a, or 2x, multiplied by f of x, and then add this with a. And so suppose that I'm actually going to label these, so I'll call this, I'll call our given, you know, number 1, and then I'll call, you know, this one number 2 over here, so at least, because we'll be using these, you know, a bunch of times when we're going through the justification of each step. From here, we want to see the pattern of how these numbers, you know, break down. So suppose that we want to see what f of 2 looks like. So in this case, what we just wrote is that we have to plug in that x is equal to 1. Okay, so f of 2, so plug in x, so equals, so f of 1, we set that was a. And then on the bottom, so plug in 1, so 1 plus 2, x is equal to 1 in this, so that'll be 3, and then f of x, which we set that f of 1, that's a also, so 3 times a and then plus a, 3a plus a, which is basically equal to a divided by 4a, which is in other words equal to 1 over 4. We got some number, but let's actually keep going and see what we get. So now f of 3, suppose we want to find the value of f of 3. So f of 3 is basically just plug x is equal to 2, so f of 2, so we said that f of 2 was 1 over 4, and now next comes that we have 1 plus 2 times 2, so that's 5, and then multiply by f of 2, which is again 1 over 4, so that will be 5 over 4, then add this with a. Then if you actually just, you know, solve the algebra from there, simplify that out, you'll get that f of 3 is actually just equal to 1 divided by 5 plus 4a. Next, suppose we continue on, keep trying and see what we get. So suppose f of 4, we want to find its value. So now we would have f of 3, so x would equal 3. So f of 3, we said that that was 1 divided by 5 plus 4a. And then divide this by, so plug 3 in the bottom, so that will be 7. Then multiply by f of 3, which is 1 over 5 plus 4a, and add this with a. It's a pretty long algebra if you want to simplify this on your own. You know, it's typical algebra stuff. But the simplification comes down to is that we have this is just 1, and then divided by 7. Add this with 5a, and then add this with 4a squared. Now, interestingly, if we were to set if x is equal to y is equal to 2, right? So, and we put this back into our given equation, number 1, then we would have, so we plug 2, so we have f of 2, then add this with f of 2 again, then plug in the 2, so 2 times 2 times 2 is 8, and then that'll be plus 8 times f of 4. And so that's just equal to, so f of 4 on the top, and then 2 plus 2, 4, f of 4 on the bottom, so they cancel each other out. So on the right hand side, we just get just 1. Then we notice that if we actually, well, in other words, you could actually combine these two together. So in other words, this is 2 times f of 2 plus 8 times f of 4. So now what we do is we can actually just plug in some, you know, terms back in. So we said that f of 2 was equal to 1 over 4, so 2 times 1 over 4. So in other words, that's actually equal to 1/2. Then add this with 8 times f of 4. So we said that f of 4 was equal to 1 over 7 plus 5a plus 4a. So 8 divided by 7 plus 5a plus 4a squared. Okay, and we said that that was equal to 1. So all that's left is that we just need to solve what a is. I'm going to skip that step because just solving for a here, that's a pretty simple step that anybody can do. It turns out you have two solutions. One of them is positive and another one is negative, but hence we're actually just dealing with, you know, positive rationals. So we one of the solutions is negative, so we can just exclude that. But by solving that, we'll get that a is equal to 1. And so therefore, just from plugging this back in, we set that f of 1 is equal to a, so thus f of 1 is indeed equal to 1. Okay, so there we have it. We just proved step 1, that f of 1 is equal to 1. So now let's actually get on to the second step. So what I'm going to do is I'm actually going to put the I'll leave this statement over here, proof that f of 1 is equal to 1, and put that as a check, and we're just going to move on to the next step. Now the second step. Second step is going to be a little bit interesting since we just shown that f of 1 is equal to 1, but maybe there's also some values that we want to see a particular pattern, just like what we did earlier with f of 2, f of 3, f of 4. So there has to be some sort of general formula we can find that we want to, utilize that. So now the second step is that we want to show the following. We want to show that the function f of x plus n is equal to f of x and then divided by, so inside the quantity is n squared plus 2nx multiplied by f of x, and then add this with 1. And then this is for natural numbers, so n equals 1, 2, 3, 4, all the way so on and so forth. I'll say 1, 2, 3, 4. So that's our next step that we want to do. So now how do we do this? Well, the simplest method we can think of is just using induction. So induction basically says you prove your base case. You afterwards suppose that you have your n equals k. Suppose that's true. Now you just have to show that it's true for n equals k plus 1. In other words, it's that same analogy with using the domino effect. So that's what we want to do, because that's actually, again, we want to find some generalization of a formula we could choose for any of the numbers. If we use induction, so by use induction, so we have to see that the base case n is equal to 1. That's true simply because we just did that from earlier. We showed that from number 2. I should also label this. I'll call this is also should be number this is number 3. I should have also left number 2 up. So let me actually put number 2 from what we said earlier. Number 2 was that we said that f of x plus 1 is equal to f of x divided by 1 plus 2x times f of x plus a. We call this number 2. And I'm going to leave this up. I'm going to leave these 3 numbers up so at least we could get some justification. So anyway, I say that for the base case n equals 1, we said that's true simply because we just showed from number 2 that just from solving all this out, then that would have been the case. Then 3 is also true. You can see this for yourself for n is equal to 1, because exactly just what we did from like the first step. That's basically the base case from there. So now what we have to do now is we have to suppose that number 3 is true for n is equal to k. Okay, so now this is where the fun part comes. So let's see, I'll put this as, now suppose n equals k is true for number 3. So from that, now we have to show that f of x plus k plus 1 is true. So we showed that. So we're saying that f of x plus k is true. Now we have to show that x plus k plus 1 is true. So here's an interesting take on this. So simply we know that by induction we have to show that x plus k plus 1 is true. So basically you just plug the k plus 1 into your input, then again show the whole thing is true by itself. What we can do is the way we can actually group this, and I'll say that for I'll put it this way. So we have that f of x plus k, and then that's already grouped on its own, and then add this with 1. We can just go back to number 2 and put this as the following. So we have this will be, we can simply just replace that x with x plus k and just plug it back here. That's the justification in there. So put this as x plus k, and then we divide this by 1 plus 2 times x plus k, then multiply by f of x plus k, and then add this with a. Actually, just put that back instead. It's now 1 because we already solved that a is equal to 1. So from here, now what I can do is we can now just replace the f of x plus k with the assumption that's true that, let's see, so I'll put this f of x plus k. If that was true, then that would have to mean that we would have that f of x and then divided by, so quantity k squared plus 2kx, and then f of x plus 1. So if we use that assumption, from there we just replace the f of x plus k with everything over here. So now f of x plus k plus 1, so we would have the following. So this way we have f of x, then divide this by k squared plus 2kx times f of x plus 1. Then I'm just going to put the division symbol. Now we just replace the, right here, we replace the f of x plus k then over here, but simply it's under division. So what I can do is just flip the reciprocal. So now what we have on the top is now, so from the top, the numerator, we would have 1 plus 2 times x plus k, then times f of x. Then we just divide this over here with k squared plus 2kx times f of x, then plus 1. Then outside there'd be a plus 1 over here. And so continuing forward, we're doing some algebra. Over here, I'm just trying to get a common denominator from the 1 over here. So we're basically just getting the same thing just like before. So we have f of x, and then we divide this by k squared plus 2kx times f of x plus 1. Simply, this side's still the same thing. Now next, again, we get a common denominator. So just by doing so, we have 1 plus 2 times x plus k multiplied by f of x. Add this with k squared plus 2kx. Then that's the quantity inside, so times f of x plus 1. And then under the denominator, it's just basically this. So k squared plus 2kx, then f of x plus 1. And then you'll see that just from the division, if you flip the reciprocal, these two terms will cancel each other out. So this is equal to f of x. Then we divide by, so this will also be f of x. I just factor out the, f of x from out there. So, and then there's also just combining the terms as well, don't forget. So after the factoring, so we have 1 plus 2 times x plus k. Then add this with k squared plus 2kx, and then plus 1. And now from here, we just simplify some terms. Well, not exactly simplify, but we can actually, we can unfoil this. And after doing a little bit of the rearrangement, well, specifically f of x comes out to the right-hand side, but then inside this expression, we can actually unfoil this, well, to some part, I mean. So now over here, after performing that unfoiling, we have k plus 1 squared plus 2k plus 1, then times x. Then with the quantity f of x, add this with 1. And so that's it, just the numerator. And so therefore we just proved that it's true for k plus 1 simply if you just go back to right over here, or right here. If you were to plug k plus 1 over here, so we have that f of x, plug in for n, substitute that as k plus 1 squared, just like that, then 2 times n, replace that with k plus 1, just like that, and then f of x plus 1, boom. We just proved that the k plus 1 case is true, and so by induction, everything is true for all natural numbers n. Let me actually, because we're already done with this part, so I'm just gonna get rid of this, leave some more, and then write some more room. So now from number 3, we have that we would have that f of n plus 1 is simply just equal to f of 1. So we just substitute this for x is equal to 1 back here. So we have f of 1 then divided by, so this would be n squared plus 2n, and then multiply by f of 1, which is, well, hold on, let me actually just write f of 1 explicitly, then plus 1. Then we can actually do some further simplification. So let me see, so I'll put back as f of n plus 1. Then we would have, so f of n plus f of 1 is equal to 1, since we just proven that, so the numerator would just be 1. Then this would also be 1. So we have n squared plus 2n plus 1, which can be further simplified and reduced to as, if you unfoil it rather, we would have that n squared, we have n plus 1 squared is equal to f of n plus 1, further implying that f of n is equal to 1 divided by n squared. Okay, and so there we have it. Well, we just showed the generalization already, but there's more of a further discussion that we want to, analyze it just after proving that. So this is the hence the conclusion that we have come to, for now. This is also for n is equal to 1, 2, 3, all natural numbers, so on and so forth. Okay, so let's actually move on to the next step. Okay, so now the third step is we just, further showed that f of n equals 1 over n squared for the natural numbers n, 1, 2, 3, 4, and so on. So now, next thing for step number 3 is that we want to prove that f of 1 over n is is equal to n squared, where, you know, just from going from that simplification, we said that that was, in other words, it's saying 1 divided by 1 over n quantity square. So now let's actually perform that. So suppose that we'll actually let x equals 1 over n. Then we just plug this back to right here. We plug this in number 3. Then we would have that f of n plus 1 over n is equal to f of 1 over n, and then divide this by n squared plus 2. Then we multiply this by f of 1 over n, and then add this with 1. So now next, let's actually let y equals 1 over x, and then we plug this back in for number 1, which is our, you know, our given. So by doing so, now we would have that f of x plus f of 1 over x, then plus, let's see, so 2, then x, and then so it will just be 2. Yeah, f of 1, which is, we said that was 1, then yeah, that would be plus 2. Then over here, this will just be equal to, the top will just be f of 1, so that's 1, and then over here is just 1, so this will be 1 divided by f of x plus 1 divided by x. And so now that would have to imply that if we say for f of n is f of n plus f of 1 over n, and then add this with 2, which is basically equal to 1 divided by f of n plus 1 over n. But it's a good thing we did this because we just have this to substitute this back in. So basically all we have to do is just actually, since it goes under the denominator, we could just flip the reciprocal. And so the f of 1 over n will cancel to both top and bottom, but we have a 1 over f over 1 over n on the, you know, there. So now we would have, we have n squared plus 2, and then plus 1 divided by f of 1 over n. Okay, notice that the 2's will just cancel each other out, so we'll have, so there's an f of n where we said that, where we just showed that f of n plus, or just f of n was equal to 1 over n squared. So here, I'll have to replace this with 1 over n squared, add this with f of 1 over n, and this is just equal to n squared plus 1 over f of 1 over n. Okay, so this is basically just a simple case of just match with match. They're both equated, so consequently saying that f of n equals what is it, 1 over n squared, that has to imply that f of 1 over n is actually just equal to n squared. And so pretty much that's it. We just finished that just like that. So we're done with step 3. So now we're on to the final step. So let's actually move on to that one. So now the final step now is we just showed that f of 1 over n is equal n squared. So it's in the form of a rational function, but we have to actually consider more, you know, rational functions that are irreducible in that situation. So that's the last thing we want to consider. So now the fourth and final step for this finding our solutions is we want to show that also there's some conditions that we need to add. So show that if q, which is equal to n divided by m, with the greatest common divisors GCD of n and m, or m and n, whichever you want to put it, equals 1. So that's a way of giving us the condition that this rational function is irreducible. And it's also dealing with positive rational functions, so we can also say that m and n are, you know, natural numbers. That then f of q is equal to 1 divided by q squared indeed. So again, it's a more general case for, you know, irreducible fractions, so that's just to consider. So just from that, so now that's the last thing we have to show, which this is not that difficult, because I wouldn't really say difficult, because you really have to more just choose whatever variable is correct to get to this, you know, proceed forward. So just from doing so, we would put x equals n, and we set y equals 1 over m. Okay, and of course m and n are natural numbers, and, you know, greatest common divisor of n and m, they have to equal 1. And we put this back in our given, so number 1. Just from that, so now we would have f of n, add this with f of 1 divided by m. So 2 times n, and then so plus 2n divided by m of, so times f of n divided by m. Then this would equal f of n divided by m, and then on the top this would be divided by, that's the top, and then denominator would be f of n plus 1 over m. So we have that. So now let's actually put in more of a substitution. We'll put x equals 1 over m, and we'll put this in our equation number 3 over here. So put in 3. From there, so we have f of n plus 1 over m. You know, it's just commutative, you know, so that's why it's just backwards a bit, so it's okay. So we have n plus 1 over m. So simply this will just be f of 1 divided by m. Then we can just divide this by, okay, so this will be 2n divided by m over here. So n squared plus 2n divided by m, then times f of 1 over m. Then this is add this with 1. And then we can actually perform some further simplification from over here. So what this gives us is that eventually if you actually just solve this out and then get a common denominator for everything, we would get that this is just 1 and then divided by n squared, add this with 2n divided by m. Well, it's not necessarily because f of 1 over m, we said that that was also m squared. So that'd be m squared on the top and then m squared on the bottom. What you could do is factor out the m squared from everything. So that'll be a 1 over m squared over here, and then the m squares will cancel, and then we get you know, the following over here. So, and then divided by m squared. And then you can actually unfoil the numerator or the denominator, and so we would get this is n plus 1 over m then square. And so just like that, now the n plus 1 over m. So let's see, so now we can actually perform some more simplification. So now we would have f of n, which we said that was, what was it? That was 1 over n squared. Then add this with m squared. Then add this with n divided by m, which that actually still remains the same. So 2 divided by m, then times f of n divided by m. Then we can say now that we have n divided by m, so the numerator still stays the same, but the n plus 1 over m, we can substitute that, but under the denominator, so flip the reciprocal, so we have n plus 1 over m squared times f of n divided by m. Then finally, that if you were to solve for f of n over m by itself, so now we start back from the beginning, so f of q, which is, we said that that was equal to f of n divided by m. Performing all this simplification and all this, you know, factoring, so we would now have the following. We would have 1 over n squared plus m squared, 1 over n squared plus m squared. I thought I said that wrong, but no worries. Then n squared plus 1 divided by n squared. And if you actually reduce this and simplify this out, we get m squared divided by n squared. Then simply just say m divided by n squared. In other words, we just showed that this is actually just 1 over q squared. And so there we are done. So you can easily check and verify to see that f of x is equal to 1 over x squared to this entire condition. And it does work, and it's the only function that satisfies it. And so therefore we are done. The only function that satisfies this functional equation is f of x equals 1 over x squared, and just like that we are done. So that's a pretty long video for, you know, a Chinese New Year special. So I hope you enjoy. I'm sorry if my rambling went on. This one was actually a tough one, I'm not gonna lie. So that's why I had to go back and forth with my notes just to validate and check that everything I wrote is indeed correct. I know when it comes to like when you're writing solving problems, you have to have that confidence, but there's this thing about me that sometimes I overthink, and that's why I always stumble my words and I always jumble. But in the end, everything worked out the way it did. So I hope you enjoyed. Hope everybody has a great Lunar New Year, or if you're not celebrating Lunar New Year, that's okay. So I wish you guys, you know, good luck, good wishes. You know, hope you have. I wish your life actually heads in the right direction. Well, in terms of, you know, happiness and then, you know, prosperity, fortune, and all that stuff. So yeah, 恭喜發財，恭喜發財 to everybody out there. So yeah, that's pretty cool if you ask me.